Okay, so apparently, as we're still settling, so to kickstart this session, from the feedback, from the questions I got in between, it seems what was a little confusing beyond necessity was a word that I use, and this word was a manifold, and it seems that it led to a lot of confusion, and it was scary, and it was not meant as such, as opposed to the other ones that I was using. The manifold was supposed to be friendly, and I'm just so used to using this word that I forgot that it might not be familiar to some of you. So, okay. Unfortunately, I don't really know which word I can replace it with, so I'll be still saying manifold, but please don't be scared. And manifold, essentially, the definition is very abstract, but it is a generalization of a curve or a surface. So essentially, one-dimensional manifold is a curve, so there's not that many of them. It can either be a straight line, folded somehow, bent somehow, or it can be a circle. Now, in more dimensions, you know what a surface is, like two-dimensional surface. It's like Rn, but bent. So it's just, if you have Rn made out of rubber and you bend it and twist it and you press it and maybe glue it a little bit somewhere, that's a manifold. So that's surface. A roof of a building, surface of a sea, something like this. Something flat in many dimensions. I don't know I don't know if I made it easier or not, but everybody comfortable with the surface? Okay, good. So I changed the background. Now we have something different pretty in the background. It's probably the most famous fractal. It's a Mandelbrot set. I'm not going to talk about Mandelbrot set, at least not much. So Mandelbrot set, yeah, okay, I said I won't, and I am. Essentially, this whole thing with the whole craze with fractals started with Benoit Mandelbrot, who worked at IBM, who picked up a picture that somebody printed and went, I think, to New York Times with it, and everybody loved the picture. So it's called the Mandelbrot beetle. And how many of you do know how this thing is generated? Okay, so this thing is generated. Can I have the screen? Thank you. If you want to see a beetle on your own screen, you write a very simple code. So you take the map, Z. Oh, it's green. Okay, I like green. Okay. So we've seen this map before, right? And then you should see if this trajectory escapes to an infinity or not. But of course, you don't want to do it, especially if you're a technician at IBM. So what you do, you just loop it 100 times. So you take F100 of Z. I guess everybody here should be able to code up a loop, 100 iterations of this map. And you see if it's larger than whatever you want, 1,000. Absolute value, of course, because it's complex. Now, if it is, you mark it red. If it isn't, you mark it blue, or whichever two colors you choose. And essentially, the technicians were just playing with computers. It was many years ago, and IBM made the first computer who could make nice pictures easily. So they wrote the simplest code they could, and to their huge surprise, the shape they saw was this. They were thinking they would see some circle, maybe something more regular. Apparently, it's a fractal, and then the whole craze began. Okay, so that was Mandelbrot set, and now that we have it out of the way, the Mandelbrot, and hopefully the manifold is no longer that scary. I was asked the question a couple of times, how does it relate to machine learning? So I kind of said it in a way. I said that it relates to gradient descent, but I guess it's not satisfactory. Oh, they were still here, so maybe it was anyway. But I will say a little more how it relates to machine learning. And I thought even about going straight into it. You know what? I'll go straight into it. Okay, you asked for it, so you'll get it. I even have slides for that. So, we say goodbye to Mandelbrot. Well, to the Mandelbrot set. Mandelbrot actually is a very interesting person himself. He very often, at least once a day, compared himself to God himself. And he ate lunch with us at IBM when I was working there, so he clearly doesn't have self-doubt issues. Well, but he changed the history. Okay, so we'll skip that. Okay. Here's something I love talking about. It's called perception. And as far as I know, at least that's what I've been told during dinner, you already heard about perception. Oh, well, no. Now I'm doing slides. Now I'm being like, more American. I don't know. So this thing, ladies and gentlemen, is a perceptron. Have you seen this picture before? The first machine learning example, actually, was a machine built by Rosenblatt in 1958. It was in some military naval institute, I believe, in the US. And it was, the first concept of machine learning that worked, actually. What it was doing, it was trying to find a linear separator between the data. And the first perceptron was a physical device. You were essentially sticking metal things into holes to mark positives and negatives, and then something was moving inside and it was trying to find a separating plane. And if it could, it could. If it couldn't, it couldn't. And then I'm not exactly sure if I'm precise about it, but as far as I know, then somebody observed that it couldn't learn XOR problem. Well, not surprised, it's not linearly separable, so you cannot do it. You know what an XOR is, right? Okay, that's just in case. I'm sorry, there'll be lots of switching, I guess. You know what, actually, let me leverage the colors. Okay, so. No matter what I do, I cannot separate it with a line. So of course perceptron cannot learn that. And as far as I know, then Minsky made a remark about it, and his power of his word was such that it caused so-called AI winter. So you probably heard the term AI winter. So essentially it was understood that Minsky said that machine learning doesn't work or AI cannot exist, and everybody who wanted to do AI was deemed a crazy man. It's interesting how history repeats itself. So the same thing happened in the Middle Ages. Aristotle made a typo in his book saying that the fly had 4 legs, and if you were at your right mind, you'd rather not question it publicly because it would be the end of you scientifically, because you do not question this. So it seems that the human nature is unchangeable, and anyhow. So coming back to perceptron, it cannot learn that. However, the question was, okay, so what it cannot learn, but if the data is nice, now I'm writing blue. I guess I don't have to explain this picture, right? It's a standard machine learning setting, positive and negative examples. So now it is linear separable, meaning I can fit a line that separates into positive and negatives. You can fit a nice line. So the question is, can perceptron always do it? And to answer this question, we'll have to see what the perceptron does. And could we switch back to the computer? I'm really sorry, but there'll be a lot of it happening. Yeah, so again, I love it. Don't you think it's beautiful? I do. Anyhow, okay, so here's the same picture, only better done. But I had fun drawing mine. And yes, here's the same thing done even better. So this is not linearly separable, and this is linearly separable. And this little thing here is called the margin. And probably you know all this because you had introduction to deep learning. But doesn't hurt to see this picture too many times. Okay, so the online perceptron algorithm. Here's an algorithm. Essentially, it loops through the points, and it has some initial position of the separating plane. It's a line on my picture because it's two-dimensional data, but in general, the plane can be anywhere. And it looks at the sign, so it has some weight vector v, and has some data point x, and it computes the angle between v and x and sees if the x is on the right side of the separating line. Okay, who got confused at this point? Everybody following? Isn't there something missing there? Bias? Right? There's just multiplication. There's no bias. And does everybody know how to deal with the lack of bias? Has it been covered? Should I repeat? I will anyhow. So because I think it's very important to be aware of it. Okay, can we go back to the whiteboard? Okay, so here's the thing. What we are trying to do, we are trying to build a classifier v tan dot x. Now I want white. Okay, so that's a classifier. Okay, who here is not familiar with the dot product? Everybody familiar with the dot product? Good. Yes. Geometric interpretation of a dot product too? Right, we know it's an angle, most specifically, multiple product of two lengths of the vectors and the cosine of the angle between them. Good. Saves me some time. Okay, so maybe I'm not necessarily I'll still repeat what I put to do. Okay, so I was trying to build this classifier. But what does it really mean geometrically? Geometrically means that I'm not looking for a separating line, but I am looking for a separating line going through the origin. So if, by unfortunate coincidence, my data is like this, I can try all I want, right? Or even more. Right, if that's my data, with the line going through the origin, I cannot separate it, and I can keep trying. My perceptor will be grinding and grinding, and nothing will happen, because my separating line should be this. Something of that sort, right? So usually there's plus b term, so-called bias, right? To shift it. Because this equation without b is an equation of a linear subspace, and this thing is an affine subspace. However, in the presentation that I had in the slides, there was no bias. And what do we do to drop bias? To drop bias, we do this little very nice trick that we drop bias by just embedding our data points and adding one more coordinate equal to 1. So we have, if I have a vector x1, x2, xn, we just add one more coordinate equal to 1. Right, you know this trick? Okay, so, and do you know what it means geometrically if you think about it? You just add one more dimension, and those points now, imagine, you're looking for a hyperplane, for a linear space, but in 2D, so it can also bend. So now, if we have more dimension, imagine this is now pulled up by 1, so it's on level 1, and here's x is z, which I just added, you can separate it. So there are two versions of the algorithm, the perceptron algorithm, and sometimes people write it with bias. And I think originally when Rosenblatt was thinking about it, he was using bias in his notation, when he was doing his analysis. But I'm dropping bias. Okay, so from now on, no bias in my notation, and we just keep in mind that the last coordinate or the first coordinate, however you please, in your vectors is fixed to 1. All right, can we go back to the slides? Thank you very much. So, okay, with that little thing now, we know everything is lifted, and if the point is on the right side of the hyperplane that we are trying to separate everything with, it's, I say hyperplane, I should probably say subspace, because now it's going through the origin. If it's on the right side, we do nothing. If it's on the wrong side, we do this strange addition rule. And this addition rule, so y is the true label, so we, so if it's misclassified, we add the weight. We add just the value of the point to v. Now, when I first saw perceptron, it's been many years ago, I was puzzled. Why the heck such an update rule? Why x? Why not x squared? Why x? And I just accepted, okay, probably that's how engineering worked back then. It was the natural thing to do. And you know, then, since 1958, a lot of years passed. And only, like, it was short, around the time I was joining DeepMind, I looked at the perceptron again, and I realized that actually went full circle. So here's a little homework, if you want, of course. Think about perceptron, and perceptron really is a ReLU-activated network trained with SGD using stochastic gradient descent. Well, unless you loop in order, but if you choose points randomly, it's a batch size one, ReLU-activated, one neural network. Isn't it ironic? We had to go through 30 years or so, even more, of trying sigmoids, inventing things. Turns out that the first guy who ever did it got it right. At least I find it very ironic in a beautiful way. All right, so we have perceptron, we have the update rule, and now I'm going to prove something to show the relationships. So I am going to prove the following theorem. Usually it's called Novikov's theorem, but I guess Bloch was also involved, so he's there. So under very mild assumptions, perceptron converges. And the mild assumptions are, first of all, that your data is not unbounded. It all sits in some disk of maybe some large radius, but it's uniformly bounded from the above. Also, the second thing might look a little bit more mysterious or not, but it says, this thing says that there's an error margin. So this thing here essentially is a projection of every data point onto the direction normal to the separating hyperspace. So this is a distance of a point xi from the separating space. Is it clear for everybody? Good, so I don't have to explain that. Great. Yeah, I know I'm asking simple questions, but you know what? I'd rather ask too many simple questions than too few. You know, I'd rather no student left behind or something like this. So then the claim is that the number of mistakes made by the perceptron is at most r over gamma squared. And it took a couple of years, it took 4 years for this thing to be proven. I guess it's just the amount of time it took for this thing to go from the table of computer scientists to table of people who cared about proving it. I'm pretty sure that computer science could have proved this if they didn't have more interesting things to do. Mathematicians don't, so they prove things. And yeah, so here's the proof. So the proof is, we start with v1 equal to 0. Honestly, usually people start with a unit vector. So, but okay, for the simplicity of the proof, we can start with 0. Yes?
So just one question. So y has to be -1 and 1, right?
Yep. Didn't I say that?
I think you didn't say it.
Okay. Thank you very much. It was a very valuable remark. So yes, in this setting, the labels are not 0, 1, but -1, 1. And that's why a misclassified point gives you a wrong sign. Yeah. Thank you very much for this remark, yes. As you see here, there's a sign, v dot x, so it's kind of implicitly, yes, but yeah, okay. It's -1, 1, yeah, absolutely. So, here's an update rule. We have vk plus 1, and essentially, it's either the previous one if the point is classified, and then we don't count errors. So we're not counting the number of steps in perceptron. We're counting the number of mistakes we make until it trains. But we know the number of points, so one thing follows from there's a quick estimate of one from another. Anyhow, so yes, let's look at the first equality, and this actually everything is written here. So let's go over our first equality. We look at the dot product of vk plus 1, which is new set of weights, times the normal vector to the separating plane. Well, it's not to the separating plane. It's that it's a true separating direction of the data. U is something that exists for the data, as you remember. So eventually, we want to find it. U is what we want to find it, essentially. Okay, so this thing, the first equality is just the definition. That's how we define the vk plus 1. Because it was a that's how it was defined, and the order is swapped here, but it doesn't matter. Dot product is symmetric for reals. Okay, and the last thing is essentially by the definition. We know that those things are bounded by gamma. That's the definition of gamma. So the first estimate is pretty much trivial from the definition. Now, that's what we got from here. Now the second inequality will be like this. So here we estimated a scalar product of the weights vector with a separating direction, and here we are estimating the length of it. So the length of it is here, and again, the first equality is just the definition. Comes from here. Any questions about this? Okay, I thought there was a question. Okay. And this inequality, is it obvious where it comes from? This is an estimate of x. It's by assumption. This is negative. The point was misclassified. So we can drop it. And we're increasing the right-hand side. Clear? Okay, so we did the two algebraic tricks. Nothing much there. No. And if we combine those two things, it's if we combine this thing, okay, one thing I should say, and I didn't. And here's kind of where comes the dynamical systems part. So now, coming from here to here, what's happening? We know that V0 is 0. So if we repeat this thing k times, we just accumulate no more than k times gamma. So here's an upper estimate, not a recurrent, but a full estimate on gamma k plus 1. Again, same thing here, precisely. At every step, we gain at most r squared. Okay, so now all we have to do, we take a square root of both sides. We combine those things. This might be a little tricky. Where does this one come from? Sorry? Yes, precisely. So this is more or less a definition of the dot product. The dot product of those two vectors is the length of this vector times the length of this vector times the cosine. Cosine is never larger than 1, and the length of u is 1, because that was the assumption. So obviously, if the cosine is 1, then there will be an equality. If not, there's not. So what you said was absolutely right. Yes, thank you very much. Okay, so, and now we have an estimate for this thing, which is this thing. We divide both sides by square root of k, and we're very happy. Okay, so here's the Novikov's proof. And in many ways, you can say it's trivial, and it is, but it is dynamical systems in spirit. So what you do is, if you think about it, you have a sequence of VNs, right? And there is some update rule based on something. So we have a trajectory. Now you do something about this trajectory. You do some estimates of how fast, and you say, this trajectory moves faster than something. So estimate it from the below, right? It's the same thing in calculus, like when you have 3 sequences to estimate the limit. So you bound it somehow crudely from below, but apparently that's enough. Then you bound it from the above. So you create some gap for the trajectory, and apparently that's all you need. So in a way, it is dynamical systems proof. And this really illustrates the point I was making. Did I use any theorem from dynamical systems? No, I used Schwartz inequality and common sense, and lots of hand waving. But in spirit, That's how you approach things in dynamical systems. So this would be, I read the proof before I tried to prove it myself, but essentially if I was about to prove it, that's how I would go about it, because it's a very natural thing to do. There's a trajectory that's bounded, let's see what's happening. Okay, so here was your link to dynamical systems. It's not the only one that I'll have, I promise, but for now it was, and I'll go to some other useful things that we might need, that we will need for sure in the future. So, yes?
So it's okay.
Yeah.
Let I use some question.
Sure.
What is your vector space?
Sorry?
And now you prove in the vector space, right? What kind of vector space? Finite dimensional vector space, or Hilbert space, or Banach space, or norm space, or something like that?
It's a very good question. So for perceptron, obviously, perceptron was two-dimensional, so it was R2. There were just holes in a board.
Just only a finite dimensional space, right?
Finite equal to 2. It was flat.
Equal to, right?
It was like a chessboard.
Because you use some property of norm in R2, right?
Honestly, I never thought about it. Okay, let me think.
Because you use a norm square of a vk plus 1 equal to norm of vk square, or something like that. Because this is a property of the norm in a finite dimensional space. Or Hilbert space is okay.
Yeah.
But not true in a general Banach space or something like that.
In general Banach space, I don't have dot product, so it's not a property of Banach space because I don't have a dot product. I never thought about it in Hilbert space, but I think it goes. All I need is Schwarz inequality. So I think I'm good in Hilbert space, but it makes absolutely no sense. Because the problem is I don't really know how to fit things into perceptron there. Maybe it does on a functional space. Okay, don't shoot me if I'm wrong, but I think this theorem is applicable in Hilbert spaces as well. And it's not applicable anywhere else because I don't have a dot product, so I couldn't, even the algorithm doesn't make sense because the algorithm computes a dot product. So as long as you have a dot product, you can do everything. And for those of you who don't know what Hilbert space is, by definition, it's a complete linear space with a dot product. Yep. Okay. So that was the question. But like I said, perceptron was in our hands. Okay, great. Thank you. I have a board. So two more things I need, I think. Yeah, two more things I need before I proceed to more complex examples. And the more complex and those things would be the classification of critical points. So like I said, we love fixed points. And I just said critical points. Because we are idiosyncratic and we have many names for the same thing in dynamical systems. And to make things even more complicated, now I'll go continuous. So I was talking, and there is a duality between the continuous and the discrete case. So now we are in the continuous world, so in the world of differential equations. And if you want, you can translate one to another. Okay, so differential equations. Now let's make it white. Okay, so you might remember the Graban-Hartman theorem and definition of a hyperbolic point. So I essentially simplified things for myself a little bit. Because I said eigenvalues greater or 1 or smaller than 1. Now what's the problem with this definition? The problem with this definition is that there are matrices which don't have eigenvalues either greater or smaller than 1 because eigenvalues can be also complex. And then greater or smaller than 1 doesn't make sense. And unfortunately, it's not about the absolute value of them, because if it was about the absolute value of them, it would be still fine, but it is about the real part of them. So we say a point is hyperbolic, and now I'm in the differential equations world, so the equation is, so the definition will be slightly different. So the point is hyperbolic if all eigenvalues, critical point, is called hyperbolic. And you know what? Actually, let me even write the differential equation. And I'm even making it autonomous. Okay, so it's gonna be a little confusing, but I hope it's not too much. All right, so now, like I said, we are in the world of differential equations. So now, instead of a map, in the previous case we had x maps to f of x, right? Now let me make it small, f of x. In this case, I have a differential equation. So I have a vector field. And I'm giving a different definition. So as you might see, I said critical point instead of fixed point. What's a critical point of a differential equation? It's such a point that f of x equals to 0. So it is a fixed point of an associated flow. Is everybody familiar with the notion of a flow? Okay, so it's important, and unfortunately, well, fortunately because it's interesting, flow. Okay, I wanted to go back, but it's not feasible, so I'll go forward or not. Okay, so a little bit of a digression or something I probably should have said earlier. This is a differential equation. Now, if we solve it, what we get is for every initial condition x0, we have a trajectory starting from x0. So what are the solutions of a differential equation? Solution of a differential equation is we have some point x0 and there's some motion, right? It's moving with time. So we can define something that's called one parameter group of diffeomorphisms, which would be gt of x. And how is it defined? It's defined in such a way that we've taken x for a fixed t. We start from an x, we go along the trajectory with a solution, and we stop after time t. And that's gt of x. Oh, sure. So if we have a differential equation, we can define a mapping for a fixed time t. Which means essentially if you watch a movie, you start it and you stop it after time t, and everything moved. That's the thing, and we call this thing a flow, or one parameter group of diffeomorphisms, I'm sorry. So with every continuous dynamics, you can associate a map, which will be exactly the map defined by the time t. After time t, and it's your choice what's the time step. How does it correspond to deep learning? It's your learning rate. The smaller your learning rate is, the closer you're getting to this infinitesimal movement just defined by the derivative. But essentially, that's the link. So you can always think whenever there's this duality, whenever you have this something in the world of differential equations or the continuous dynamics, you can always convert it to discrete dynamics by saying after time t equal to 1, where t is very arbitrary. Okay. And why am I introducing this duality? Because usually it's easier to work with differential equations. Differential equations, you have tools in differential equations that you do not have in discrete dynamics. So sometimes it's just much more convenient to work with this, but there are some caveats. All right, so the definition is a critical point, x0, is called hyperbolic if the real parts of all the eigenvalues are non-zero, either larger or than 0 or smaller than 0. How is it different? You remember, in the other case it was 1. And the relationship is based by the exponent, and if you remember how to solve the linear equations, if you have a if you have a differential equation and it's linear, you solve it by essentially taking the exponent of the matrix. So once in the matrix will correspond to e to power 0 is 1. That's where your correspondence is. All right. So it turns out that the classification of critical points in differential equations is pretty simple. And then, if you have hyperbolic points, they essentially can be the following. Both eigenvalues real and smaller than 0. The point is attracting. It's called a node. Okay, and this thing can be a little blurred because, as you remember, this is a linear, like a straight node, so this means the derivative diagonalizes. As you probably remember from linear algebra, not every matrix can be represented in diagonal form. Jordan canonical sometimes has things called Jordan cells. So if you have a Jordan cell, which would be 1 lambda, even the other way around, then you will get slightly different picture, but topologically it is the same. And I wanted attracting, so this. Topologically it's the same thing. Everything flows here. So that's the dynamics. And this is called a node or a sink. Well, a node is both ways. It's a sink because it's a sink because it's attracting. Now, these are the eigenvalues which are smaller than 0, obviously, if so. The other way around would be this. It's still a node, but you can call it a source, because now it's repelling. Everything is flowing out of this thing. Okay, so those are the simple things. Both eigenvalues smaller than 0, both eigenvalues larger than 0. Another case is this is a nice one. It's called a saddle. So why is it more interesting than the previous one? The previous one, all the trajectories were more or less the same, right? This one is much more interesting because those two that I just drew are special. Every other one will look like this. Right? So in a sense, those two are special, and they are called separatrices. Jet lag kicking separatrices. One separatrix and two separatrices. Okay, I think it's the first time I said it in English. Anyway, separatrice in Polish. Yeah. So, and the name comes from the fact that they separate the dynamics. And by the way, we've seen this picture before today, right? This is unstable manifold, and this is the stable manifold. And now there are only two of them. Those are neither stable nor unstable manifolds because they don't go through the critical point at all. So that's a saddle. And interestingly enough, this is all that can happen also in higher dimensions if you think about it. So I covered all the situations with real eigenvalues, but I didn't go into complex. And now imagine that's your derivative, that's your linearization, right? A complex Jordan cell of dimension 2. Now, if the point is hyperbolic, so say A is greater than 0. And this matrix, what does the matrix represent? Represent the situation where lambda 1, 2 is equal to A plus minus bi. So A is the real part, and B is the imaginary part. Is everybody familiar with that? Okay, good. Who's not familiar with that? Hands up. Enough. Great. Okay. Who's not familiar with the notion of an eigenvalue? Okay. No. That's not your problem. That's my problem. And you know what's the best way of dealing with problems? Ignoring them. I'm sorry, I cannot explain eigenvalue. Unfortunately, you just have to take my word for it. Now, there's just no way I can make Jordan canonical in 5 minutes. So my true apologies to everybody, but it's take linear algebra, and after a year you'll know what it is. This being said, linear mapping. Does anybody in the room not know what a matrix is? Good. Okay, linear mapping. Stay with me. I can do it. I can do Jordan canonical without a year of algebra. Yes. Thank you. Okay, it turns out that the right system of coordinates, a linear mapping, can do only a couple of things. There's a full classification of linear mappings in R2, and it generalizes to higher dimensions. So essentially, if you have a linear mapping of a plane, all we need to know is what will happen with the spanning two vectors. If we know where those two vectors go to, everything else is determined by it. So what can happen? First of all, they can get longer or shorter. So it can shrink and increase in some dimensions. And the eigenvalues then tell you that this thing gets multiplied and this thing gets what numbers it's multiplied by. Then what it can do, apparently, it can do this to those two vectors. It's a shear. That's called a Jordan cell. One is following another. So in the right system of coordinates, every 2 by 2 matrix can be represented either as, in the right system of coordinates, you have to find those two vectors. But you can either, every linear mapping can be either represented as this, or as a, that's a shear. This one, like a scissors. One falls onto another. And there's one more thing you can do, and that's it. And the other thing is rotation. You just rotate the picture with some shrinking and or shrinking or expanding. And this is pretty much the three things that can happen. And then this thing says A, B minus B, A. And if I have a matrix like this, I can always represent it as R, which is a scaling factor. And then I will have cosine phi sine phi minus sine phi cosine phi. Is it clear that I can do it? I can always scale those up to such a thing that those two in second power add to 1, so I can find such an angle phi that I can represent it as its way. And this thing, this matrix here, is a rotation matrix. So this matrix, what it does, it rotates the plane by the angle phi, and R scales it. These are the only things that can happen. Thank you very much, Jordan Canonical in 5 minutes. Ladies and gentlemen. Okay, coming back. So what is happening if the linear part of our vector field is a rotation? Then it turns out that the trajectories will look probably as you expected, as logarithmic spirals. If A is larger than 0, and otherwise it will be going inside, and B gives you the rotation speed, so of course it could be rotating the other way, depending on whether B is positive or negative, you know, whether our phi is one way or another. And that's pretty much what can happen. That's all that can happen. We can have a node, sorry? Okay, thank you. Okay, so it can either be a node, a saddle, or a focus. This is all that can happen. Okay. Why do I need it? Because now, let's look at the following situation. I'll manage. Okay, so I was asked the question, and what's happening when we are not in a Grobman-Hartman situation? What happens if we are in the following situation? So what are the eigenvalues of this matrix? What's the linearization matrix? Okay, so it's a tricky question. So when I was still a professor, and when I was still young professor, I very much enjoyed, and to my excuse I can only say I was 21, so you know, you enjoy certain things. So one of the first test questions I was giving my students was solve the equation. And plenty of solutions were, well, etc., right? So people would expand it and use the formula for the quadratic equation instead of just writing x equals 5. I thought it was funny then. Maybe now I wouldn't do it. Another question that we used to do with my friends was find the Fourier expansion of, or Taylor expansion of x squared, things like this. So essentially the answer is you don't need to do anything because it's already there. So here's the same thing here. This thing is already Jordan canonical. You know, no need to compute the eigenvalues here, because what's your linearization? Your linearization matrix is right? So what are the eigenvalues? Anybody? What are the eigenvalues of this matrix? Okay, the eigenvalues of this matrix are purely imaginary. And for the sake of the argument, I'll prove it. If it's not obvious, it had better be. What's the definition of an eigenvalue? Eigenvalue is such a value that if you take matrix A minus lambda I, that's the definition of an eigenvalue, right? And we call this equation a characteristic polynomial, and we solve it in lambda. Okay. So let's compute the determinant. This is our matrix A. A minus lambda I. And I'll use the notation that, or you know what, I'll keep it simple. What's the determinant of this thing? Well, let's plug in. So far so good? No. I presume everybody knows how to compute the determinant of 2 by 2 matrix, right? What are the solutions of this equation? Precisely this means. And if it doesn't scream I don't know what does. That's where the I came from. Because people in the Renaissance realized that this equation had no solution, or that this polynomial had no roots. And I was exactly defined as the roots of the... This is a quadratic polynomial, so it has to have 2 roots, and those roots are I and minus I. Good. So the eigenvalues of this linearization of these differential equations are I and minus I, so x dot equals y, and y dot equals minus x. And yes, so we are not in a Grobman-Hartman situation. We are dealing with our first non-trivial dynamical system. What do we do here? We cannot use the classification. We have to think a little bit. So there are many ways you can approach this equation. And one way to approach this equation is to say that it really is Newton's equation. Because I can just ignore the first thing for a second, and I can plug in that y is x dot. So I could write this thing as x double dot equals minus x. Right? All I did was plugging in y is x dot. So if I take y dot, it's 2 dots. Dot plus dot is 2 dots. That's why Newton used this notation. And this is nothing else but Newton's equation, because the thing on the left-hand side is the acceleration, and the right-hand side is minus x. What physical system does it describe? Anybody? Sorry? It is a linear equation of degree 2, but what physical system does it represent? It is a very nice system. It's a harmonic oscillator. It's a weight on a spring. The force on the right-hand side is proportional to your displacement. So it's the simplest thing studied in physics. Or a perfect pendulum. Now, a pendulum is a little bit tricky because it's not exactly this, it's the approximations, the so-called mathematical pendulum versus physical pendulum, and perfect pendulum, non-perfect pendulum. It actually leads to one of the most beautiful things that I wanted to present today, but I won't because I don't have time. It's called the Brachistochrone equation. Anyhow, so this thing is a physical interpretation of this equation. What will be the solution? What's the motion of a pendulum or a harmonic oscillator? Sinusoid, right? If you look at the graph, if you have a weight on a spring bouncing up and down, and you attach a pencil to it, and you move a tape, and back you got a sine. Okay, but that's just my claim. So say I. Should you believe me? Of course, yes, but how do I solve this equation? Okay, so here's the thing. I always told it to my students. The best way to solve an equation is to guess the solution. That's fantastic, especially if you know there's only one. And there's only one problem. You need to be a genius for this. And plenty of things were solved in mathematics because some genius came and just guessed something that nobody else could. A prime example of this would be Srinivasa Ramanujan, right? He was just coming and guessing things, and he was right. And he himself couldn't tell how he was doing it. A couple of other guys, von Neumann also was doing things like this, but Ramanujan was like beyond anybody. Anyhow, so I'm just guessing. Okay, did I guess? Right? I'll be even more extravagant. I'll put some R in front of it. Is it still good? What's the derivative of a sine? It's cosine, right? So it adds up. The derivative of x is y. What's the derivative of y? It's x. Good. Now, you could challenge me, and you would be right. Still good? I can do a phase shift. And that's it, I'm done. Why am I done? Why? Because I presented you a couple of solutions, but they're all inclusive. This solution depends on two constants. I cannot have more than two constants because I have two equations, and we have a theorem that says that the solution of a differential equation is unique up to initial conditions. So I have two initial conditions because I have to determine x and y, and I have two decision variables, r and phi. But what does it mean geometrically? Geometrically, it means this. When I'm choosing my starting point, I am choosing the diameter, so how far I am from the origin, and the angle phi. From then on, I just keep moving. So my initial conditions specify a point in a plane. From then on, I'm just moving along a circle. And that's it. That's pretty much it. So what dynamics do we have here? It's a very interesting dynamics because it's none of the described before. And that's a dream of the King of Sweden or Poincaré. It's a center. Every trajectory is a closed trajectory. Every trajectory is a circle. What is the problem with it? The problem with it is that usually in the real life, so if I'm an engineer, I design my system, and my system of equations has some forcing. So if my system has any mu x plus y minus x plus mu y, if there's anything linear forcing convergence and divergence, I'm using Groveland-Hartman tells me I can ignore the dots. My linear force is enough. That's what my system will behave like. I'm designing some circuit to run. I'm fine. But if those are gone, I cannot ignore the dots. The dots will determine whether the thing is stable or unstable, if it pulls or pushes things. And it's a huge difference, right? If you're an engineer, probably you want to have a pull. If you start your machine, you don't want it to heat up until it blows up. You don't want the voltage in your oscillator, in your engine. If your engine is running and it's turning, you don't want your voltage to go up and up and up, because after a couple of weeks it will blow up. So if you're an engineer, you want a thing called stability, meaning essentially, and that's where I was heading with all this thing, probably one of the most useful notions from dynamical systems is a stability. it doesn't matter what your solution is that much too much as long as you cannot prove the stability of it. Meanings, and to give you another example, it makes a huge difference if your ball is in this position or in this position. In both cases, it will not be moving, but in this case, if the wind blows, first of all, it wouldn't feel it because it's in the hole, so it's isolated. But even if there is any wind and anything goes in, you would have to blow really hard to get it out of the ball of the ditch. This one, any slightest pressure and it falls off. So this one is unstable. So we don't like solution like this. This can be the most beautiful solution. And the problem is, why do we care? First of all, there can be a little perturbation, but B, no matter what we do it on a computer. Computers don't work with mathematical formulas. Computers work with integers, essentially, because we have finite precision. We can be deluding ourselves, telling, oh, we're using floats, we're using reals. No. There's only defined granularity to which we can go with any computer in the world. And therefore, no matter what mathematics we're doing, it's only an approximation. So, unless we are sure that we're not only right, but there is some margin of error around what we're doing, we're in a bad situation. And I'm going to talk a little bit about what you do in situations like this. But in general, verifying center focus problem is insanely hard. And it has no solution. It's still an open problem. I know some people who claim to have a solution to this problem, but they were bitterly wrong. Okay, so stability, and you might have heard also about a thing called the Lyapunov function. Have you? It is used plenty in dynamical systems, actually. I'm sorry, in deep learning. So it's good to know what it is. All right, stability. We say, and again, I'm not going to write it you can find it all on the internet, it just makes no sense. So I'm just giving it to give you the notions. There are two notions of stability, both very important. Asymptotically stable. Stability. And Lyapunov stability. Okay, what's an asymptotic stability? Asymptotic stability means this. A solution of a differential equation is asymptotically stable if, here's this solution. Actually, let's make it colorful because it's this D solution. So a solution of a differential equation is asymptotically stable. This means that for any solution, there exists a neighborhood of this solution such that any other solution starting from that neighborhood will converge to this solution. Everything glues to it, tending to infinity. So is 0 an asymptotically stable solution here? No. Also, this solution, this separatrix is not stable because this one runs away from it. But this one is stable. If you start from here, everything converges to it. Very nice and lovely, asymptotically stable. We like solutions like this a lot. That's why it's good to have a history. Is the 0 here asymptotically stable? Yes, it's pulling everything, it's a sink. This one is unstable, pushes things away. This one is stable, doesn't matter, it's a curvilinear thing. Everything will collapse. Where's my here. This guy, the way I drew it, is it stable or unstable? Unstable, right? It's pushing everything away. But if I was winding in the other direction, it would be stable. So a focus can be also stable or unstable. Focus in many ways resembles a node. It's just there's more mixing. So, you know, a node is when the water is flowing smoothly in your sink, and sometimes it's rotating and like, you know, a little whirlwind. So that's a whirlwind situation. So that's asymptotic stability. Now, Lyapunov stability is something slightly different. Lyapunov stability means there is some band around your solution, and we know that we start from a small neighborhood, will not leave this band. So a solution can go like this. But as long as it stays inside the band, if they don't differ by too much, it's Lyapunov stable. Do we see the difference? The difference is, for example, this thing is not asymptotically stable, it's Lyapunov stable. And if I distorted this picture, which I can do, and I will, I can always change coordinates in such a way that those things will become ellipses instead of circles. You see why I have why I might need a wider band, because this solution will go away quite far. It will the distance will become this distance. It will become larger, right? But it will not go to infinity. It stays within some range. So it is Lyapunov stable. So it's always good to know if there is a stability or not. Okay, now I have to switch to this one. Okay, so I have half an hour, right? Good. That's all that I need. All right. So I'm headed towards the Lyapunov functions. Before this, however, let me go to my favorite example. And I'll show you something that, in fact, is a Lyapunov function, but we'll not call it like this. So, yes, I solved this thing, and I'm very proud of myself. I guess the sign. However, there's another thing I could do here. I would try to construct something called first integral. Does everybody know what a first integral is? Who doesn't know what a first integral is? Good. I'll say it in a moment. Does anybody know why first integral is called the first integral? Good, yes. So, as you might have observed, in mathematics is very idiosyncratic and there's lots of tradition in it. In particular, we refer to the solutions of a polynomial equation, polynomial equal to 0, as roots. Now, if you really think about it, they are not roots. Roots is an operation of a square root, of a third root. Why are they called roots? Because in the old days, people believed that you could find those. You can find those things by using roots for second-order polynomial, some expression involving roots. So people thought that they would be able to express any solution using roots. Comes Abel, Ruffini, and Galois. Turns out, nope, no such luck. First, it's not elementary function, but still, it stayed as a relic. Same thing with integrals. People thought, you know, integration is an inverse operation to differentiation, so we have a differential equation, we'll solve it by integrating. So in the old language, solving a differential equation is called integrating it. We can integrate, it means we can solve it, although it's usually not done by means of straight integration. So there was this little digression to let everybody rest from the overwhelming mathematics. And we're going to look for the first integral. So what is a first integral? First integral is function such that so it's a function that's constant on the trajectories, whose value is not changing as the time progresses. Here's a dot, it's the differentiation. So it means that h on x of t, y of t, is constant. Does it make sense what I wrote? I have a function of two variables. If I plug in a trajectory, it becomes a function of time. So it makes sense to differentiate it with respect to time. If I differentiate with respect to time, if it's constant, it means the derivative is 0. How do I compute this thing? What is exactly h dot? Well, by the chain rule. Does it make sense? Good. Can anybody guess a first integral for this equation? Which is? Precisely. It's the second power of a metric, or a metric itself, but I don't like square roots. They're ugly. Let me write it nicer. It's the distance from the origin. We know that trajectories are circle, but let's verify it. Fantastic. Well, we wanted 0, we got 0. Presto. Okay. All good and fine. And now, something really useful for the community. There's a lot of papers published which do a horrendous mistake, in my opinion. Well, they tell you something, but I will not quote you the papers, but they exist and they've been published. And they do the following thing. And then it was pointed out by Ian Goodfellow at New Rips when he was doing a tutorial on GANs that this is a huge fallacy in the methodology, but since when such things stopped anybody. So, once again, we have this system of equations. It's a really important example. So, if you were not paying attention, you might start now, because it's a really important example in deep learning. We have this system of equations, and we already know the trajectories are circles. Now, let's be deep learning about it. How do we solve those things? By Euler's method. So, what's Euler's method? Euler's method essentially means we take point x and we take a mapping x goes plus v of x, where v is our vector field, or to keep the notation plus f of x, and there's some learning rate. Let me even make it clearer. Okay? This is our update rule. Instead of following the trajectory of a gradient, we just keep adding gradient. That's a gradient descent. So that's precisely what we do. Okay, good and fine. So here's our gradient. Well, not a gradient in this case, but this is our update. Let's follow the trajectory of the update. Okay, so x goes to x plus mu y goes to y minus mu x. I don't care what the learning rate is. That's my update rule. So let's look at our first integral. For this thing, was constant. You're on a circle, you start on a circle. Let's see, and I'll even use a different notation, which is very useful, the images. Let me see how the value of this function changed after one update. So now h of x hat, y hat equals the following. Right, so this cancels out. But the rest doesn't really seem like it wants to cancel out. So what happens? Well, what happens is is it too fast or is it clear? So the value, and this happens to be see the problem? If we approximate this system with a discrete step update, we get very different behaviors. This one is Lyapunov stable center. This one blows up to infinity exponentially. No matter what your learning rate, unless you're changing it, this thing will blow up exponentially because at every step the value of your distance from the origin will multiply by mu. So it's absolutely forbidden to do the following. Sometimes people do theoretical analysis of the convergence of the algorithm. And they say, you know what? We can change choose initial conditions as we please. And then sometimes if you choose your initial conditions, you can set some things to 0, you can solve something that's unsolvable. If you don't prove the stability, this is useless because you already did an approximation by doing this. So even if your numerical precision was infinity, just by the very virtue of what you're doing, if your algorithm inside the computer does stochastic gradient update, it adds gradient, it doesn't follow trajectory, your result might be useless because the behavior of those two things is messed up, unless you were able to prove some stability. And I couldn't prove any stability because I only have Lyapunov stability. And I broke it by this approximation. So I think it's a very important example. Okay. So I have 15 minutes left to do Birkhoff-ergodic theorem and a couple of other things, and I'm skipping Birkhoff-ergodic theorem. Actually, I'm not going to use it anymore. So I'm switching to a computer now. So I'm fine with it frozen. Such a, it's a suspenseful moment. That's where it freezes. Mic drop. Now, actually, if you could unfreeze it, it would be nice, because I just realized I'll need it. So this is going to be my be careful what you wish for moment. Everybody was asking for applications in deep learning. At your service. I have slides, and I'm not afraid to use them, and they're even flipping by themselves. Hopefully they were scary enough. Okay, can I have the board just for a tiny little bit? I'm sorry, of course I said switch, so it's my fault, but I'll need this one just for a tiny little second. 10 minutes or 15 minutes? Okay, now feel free to leave. Anyhow, so let's say we have a neural network. Yes, the moment we've been waiting for. Neural network. Okay, you should be careful with those words actually when you're a speaker. So a friend of mine was presenting some result at a seminar. You see where I'm heading with it. So this guy was presenting some very complicated proof, like for 5 hours. There were like seminars every week, and then at some point he does this, sends it from to us. Okay, and now the thing we've all been waiting for, and somebody says, you mean we're finished finally? Okay, but no, we're not finished finally. And here's a neural network. Ain't she pretty? Anyhow. Yeah. We have some weights, we have some weights, we have some weights, we have some weights. We're very happy. Okay, now we want to train it. And there's a big question, when you train your network, how to initialize the layers. And it's a big problem. How to initialize them? Well, there are some kind of recipes, but essentially, it turns out that dynamical systems have some application here. So what you can do, you can apply dynamical systems here. And this thing is called information propagation, and I'm going to give you a very mellow and nice and friendly version of what it is. And this is the picture. So what I'm going essentially to assume is the following. I am initializing all the weights from some Gaussian distribution. Does everybody know what a Gaussian distribution is? And I'm going to use interchangeably normal or Gaussian because they are synonyms, and I like synonyms. So every term here is from some Gaussian, and I am assuming that they are all Gaussians with the same distribution, so they are essentially and of course I have biases, so weights are drawn from this distribution, biases are drawn from this distribution. And that's all I can do. And I'm also assuming that this whole thing is large. How should I choose sigma W and sigma B for this thing to behave nicely? Now, if I may ask, can we switch to the computer now? Thank you very much. As you see, those slides are made especially for you. There's a date. Okay, so I'm going to start with some real basic facts, but maybe a little refresher. So we all know, or we all should know, that the integral of a product is not a product of the integrals, right? You cannot do it. A sum of integrals, integral of a sum is an integral of sum. An integral of a sum is a sum of integrals, so integral is a linear operator. Unfortunately, the integral of a product is not a product of integrals, or maybe fortunately, because otherwise we wouldn't have a job, because mathematics would be trivial. And it's not, at least not for me. So, however, sometimes an integral of a product is a product of the integrals, and it's precisely when the random variables are independent. So that's my favorite definition of independent random variables. Independent random variables are such functions that the integral of the product is a product of the integrals. If you didn't know it, it's a useful thing to know. Okay. I hope I don't have to prove it. More or less definition. A lemma. So I can just sit back and relax and you read. At least I'll sit and read. Okay. So, is it obvious? If I have two Gaussians and I take a linear combination of them, it's all linear. And that's how the variances behave. Can I move on to the next slide? Just a preliminary, but I'll be using it. So, the sum of random Gaussians is a random with a mean, which is the sum of means, and the variance, which is the sum of variances. No, this is a variance, it's not a standard deviation. So sigma y is a standard deviation, and this is a variance. I'm always confused about it in the notation. I always have to check on Wikipedia. Okay, so this was. Now, there will be some notation. This is not a prime, it's L. Why L? Because L for layer. I know L is a bad letter, it looks like 1, it looks like prime, but still, layer. Anyhow, okay, so, and the convention is, if it's a vector, it's bold. If it's a matrix, it's uppercase bold. And if it's constant, it's just a letter. I try to stick to it, so that's why the bolding and unbolding. And XL is the input to the ELF layer, and ZL is the post-activation, to be more, it's a pre-activation. So ZL is something that goes into the activation function. It's what goes into the linearity. So it's a very theoretical setting, and I'm not even saying what M activations are. What I'm assuming is only we have an input, we have a linear layer plus bias, and then we run it through some activations function, so there's some nonlinearity, and this thing is this convention that this means the function applied coordinate-wise to a vector. I'll multiply something by a matrix, it's a vector, I by bias, coordinate-wise, same thing, and then it's, I got stuck, and then and then I apply the activation. Okay, so it's just a notation. Now, W and K are the are the weights, are the terms of the matrix, and they're Gaussian, as I promised. And that's the distribution. And actually, I lied to you a little bit because I said W sigma W squared, and they're divided by K. Doesn't matter, it's just the dimensionality. Don't pay attention, not very important. And here I'm just introducing more notation. So this thing, x hat, you've already seen it. So it's a dynamical systems convention. Hat means an image. So I apply this mapping. And, well, everything's straightforward. The last thing I do, I define two mysterious quantities. I define Q, and I define H. Okay, so X is in a k-dimensional space. The layer doesn't necessarily have to go from the same dimension to the same dimension. We don't care. So this thing essentially is the length of a vector X, image of an X. And this thing, I just pulled it out of my head because I'm so smart. Not me, the authors of the paper. It's not my result. The proof is mine, and that you're going to see, because the paper, unfortunately, was, well, it was a great paper, but it was written by physicists, so it was not mathematically sound. There were some hand-wavy arguments there, and we wanted to make sure that it was holding together. So that's my idea of what rigorous is. Okay, so this quantity is precisely pulled out of the hat. It's a function of t defined by this formula. Now, if you really look at it, you can see that this is a density of a Gaussian, kind of, sort of. But still, it's just the definition of H. Okay, preliminaries behind this. Another lemma. I like lemmas. This is a lemma. It says that if X is a Gaussian, and we run it through the, if we run this a Gaussian random variable through the activation second power, we get an H on the outside. It's not obvious, wasn't obvious to me. Simple calculation. So by definition, that's a definition of the expectation, right? I'm doing a substitution in the integration by a substitution. That's my H. No doubt here, right? Okay, I just need a lemma. Here's a theorem. Well, it's a theorem. It's not a theorem from the paper or from what I'm saying, but probably everybody knows it, but if not, it's a very useful thing to know. It's called Chebyshev's inequality. Does everybody know Chebyshev's inequality? It is a very, very, very important inequality in probability, and essentially, it's wonderful because it assumes absolutely nothing. It follows from the very definition of mean and variance. Nothing more that you need. So this holds for absolutely any random variable in the universe, and it seems to be very weak, but a lot of great things follow from it. And if you wonder how to prove it and you don't know, it's a great exercise to do at home. If you have some problem, look up the Markov inequality. It's a simple consequence of a Markov inequality. And even more surprisingly, Markov inequality solves plenty of big problems in probability. Okay. So now we have a proposition. And the proposition says that the probability of X being close to HQ, so see what I'm doing here? Of course, I could just say it's a formula, but let's go back. What I'm trying to do the following. On one hand side, I'm pushing some input through a layer of a neural network. And I'm using some probabilistic tricks to say that if the layer becomes very wide, then this thing, which is nasty, it's some multiplication by linear functions, activation, and so on, can be approximated nicely by some integral formula. Integrals are nice. It's a functional formula. Mathematicians don't like series. Mathematicians like integrals. Integrals are nice. You can do something with them. Sums are ugly because they're infinite. Integrals are nice. So I am going into some functional equation. And the claim is that the norm of this thing, and this is the norm of a signal passing through a layer, can be approximated by some functional expression depending on Q. And you remember Q was some derivative of this variances of things. Does that make sense so far? So see what I'm trying to do. I'll try to see how the length of an input changes. And probably you guess what I'm trying to do. What we don't want to happen is, we don't want the network to blow things up. If it's a deep network, and you put in a signal, and this signal becomes larger and larger, it passes through layers, and even if you have like 50 or 200 layers, and people do that, we don't want the norm of the signal to blow up to infinity and shrink to zero. You want to have some reasonable signal on the outside. So if you initialize things, you want to keep things in moderation, so more or less, you want, as you iterate through the network, to have something that's not collapsing to zero and not blowing up. So essentially, you want to have a neutral critical point. You don't want to have a sink. You don't want to have a source. You don't want exploding gradients. You don't want vanishing gradients. Now, I quickly switch to gradients, but it's the same thing because you can go to backprop to the same network. It will be the same thing. If you're going backwards, you don't want your forward path to blow up or shrink. You don't want your gradient to blow up or shrink. That's the same thing. Okay, so there is this approximation, and I'm running out of time, so here's magic. I like it because it's mine, but you don't have to read it. The slides are online, so if somebody doesn't believe me, go for it. Here, you know, I'm applying Chebyshev's inequality, and I'm using this fact that this thing is really a mean, so I can use Chebyshev's inequality. I need a mean in Chebyshev's equality, so I prove that this approximates a mean. I'm happy. So I know that more or less I can approximate x with this thing. And Q is a measure of how large x is. So here's a corollary that I really like. Q, I'm reminding you, is a function of the norm of the activations at the elf layer. And I'm claiming that now this formula holds, and it's a dynamical system. I have a function, and it's highly non-trivial operator. It's an integral operator. The next value of Q is computed by plugging Q into this complicated linear operator. So it's highly nonlinear dynamics. Highly non-trivial dynamics. It's defined by the integral formula, but it's a well-defined function. It doesn't have a simple formula, but it's even more interesting that way. Here's a really non-trivial dynamical system on screen in front of you. And I even have precise estimates, so if somebody needs the stability, here it is. Everything estimated. Good and fine. But now, what's really interesting, if I plug in, as you saw before, this thing depends on the activation. Of course, this thing has to depend on the activation. Depends on the activation, doesn't depend on the width of a layer because we kind of assume it's very large, so we pass to the infinity. We use the law of large numbers implicitly. So essentially what I did on the previous slides, I never called it this way, I just invoked Chebyshev's inequality, but I really proved in between the lines the law of large numbers. But what would happen if we plug in a ReLU here? Well, first of all, ReLU will kill this part because ReLU is 0 for negative values of s. So now it will be integrated only from 0. And this thing will disappear and s will be in second power because ReLU is either 0 or identity. So for ReLU, we got this. And it happens so that this integral can be computed. This is a definite integral, and you can compute it. And that's the value. So now, lovely thing. We got a dynamics, which is linear dynamics now, but that's only for ReLU. And what does the dynamics tell us? The dynamics tell us that for ReLU, we don't want this thing to shrink, we want this thing to blow up, so we want this thing to be 2. And that's pretty much it. We want the sigma to be square root of 2. So Q stays what it is. Otherwise, if Q squared W is larger than 2, this thing will blow up to infinity. We have exponential growth. If QW squared is smaller than 1, this thing will collapse to 0. So the good initialization would be to choose for values sigma w equal to square root of 2. And this is just a very simple version. You can go much farther with it, because then you can also look for how the correlations between things collapse. So you can do the same thing, but for the pairs of vectors, and you end up with a C value, and everything gets really complicated, but somehow we managed to do the C dynamics, but this is the simple part of the dynamics. Okay, so you had your application, and I'm out of time, so thank you very much for your attention. Thank you very much for coming, and thank you very much.
So, time for some questions. Is there any questions? No?
I have a short question. Did you also put other activation cases to not only ReLU case?
Yes, of course, we played with everything. In most cases, you can do the estimates. Sometimes you just plug it into your linear solver because you can do it. We played with Taylor expansion, so we have a couple of heuristics actually that work in those cases as well.
Nice. Thank you. Actually, we need some more extension.
So any more questions? No? I actually have many questions myself, but so I'm going to ask only one. So I wonder about your definition of Q, because I didn't follow everything. So first of all, is Q random?
No, Q is well defined. You have it here.
Is X random?
X is your input. S what comes into your network.
All right, okay. So this is not random then. All right, that's fine then. I'll sort it out later. No. So my second question is, this is back to the proof of Novikov. Yes. long. I wonder. So you showed us that the update is something like plus y times the x, right? That's the update to the. Plus y.
You're just adding the x to the weight.
Yeah. So my question is, can I introduce some learning rate?
Yes, absolutely.
And what do I have to change in the proof? That's my question.
And my answer is nothing.
Is it correct that I can just absorb into gamma?
That's a big mystery of the proof of Novikov. If you plug in a learning rate into the proof of Novikov, it cancels out. It absolutely doesn't matter. It's irrelevant.
Okay. Right,
it's shocking. Okay. It's really shocking, but it is true. So, I just presented a simplified version, but the learning rate cancels out. It's still the same number of steps.
All right, so if there's no more question, then let's thank Greg again.